All right, let's talk about something that gives a lot of electronics students nightmares. AC circuit analysis. I mean, it's a maze of shifting sine waves and, let's be honest, the math can be brutal. But what if I told you the key to making it all simple was a number that people often just write off as, well, imaginary?
So let's get right into it. Why is this so hard in the first place? You know, with DC circuits, everything's nice and steady. But in an AC circuit, the voltage and current are constantly changing, swinging back and forth in these sine waves. And to make it even worse, they're often out of sync. One is leading, the other is lagging. Trying to add those shifting waves together is a real mathematical headache.
Visit youtube.com/avidsystem and don't forget to subscribe.
And that headache has a name: trigonometry. Remember all those messy formulas from math class? Well, to properly combine two AC signals that are out of phase, you have to dig all of them up. It is a slow, painful process where one tiny mistake can throw off your entire calculation. It's just not practical for designing the complex electronics we all depend on.
But what if we could just sidestep all of that trigonometry completely? What if there was a mathematical tool so powerful, so elegant, it could turn this whole complicated mess into simple arithmetic? Well, there is. And honestly, it's one of the greatest shortcuts in all of engineering.
And this is where our hero enters the scene, the complex number. Now, unlike the regular numbers we're used to, which just live on a simple line, these guys exist on a two-dimensional plane, and it's that extra dimension that holds the secret to simplifying AC circuits.
So what even is a complex number? Think of it like a coordinate on a map. It has two parts. You've got the real part, which tells you how far to go left or right along the horizontal axis. And then you have the imaginary part, which tells you how far to go up or down on the vertical axis. Put them together, and they point to one specific spot on this plane.
Okay, I know what you're thinking. That word, imaginary, is just awful. It's super misleading. It was basically a historical accident, just a terrible branding decision from centuries ago. For what we're doing, it is not imaginary at all. It's just a name for that vertical axis, and trust me, its function is very, very real.
And this brings us to the absolute star of the show, the letter J. Now in electronics, we use J instead of I so it doesn't get confused with current. But let's completely redefine what J means right now. Forget all that stuff about the square root of -1. From this moment on, I want you to think of J as one simple command. Rotate counterclockwise by 90 degrees. That's it. That's the whole trick. Let's watch this command in action. Say we start with the number 5, just sitting there on the horizontal, real axis. Now we multiply by J, we follow the command, and rotate it 90 degrees up. Boom, we're at 5J on the vertical axis. Let's do it again. Multiply by J, another 90-degree turn, and now we're pointing left at -5. One more time gets us to -5J, pointing down. And a final multiplication by J brings us right back where we started. It's a perfect little rotational system.
Okay, it's a neat math trick, but how does rotating numbers around a 2D plane actually help us with real-world AC circuits? Well, this is the magic step. This is where we connect this abstract math to physical reality using something engineers call a phasor. And here it is, the big aha moment. An AC signal has two key properties, right? Its strength, which we call magnitude, and its timing, which we call its phase angle. Well, guess what? A point on the complex plane also has two key properties, its distance from the center and its angle. It's a perfect one-to-one match. That point on the plane becomes a perfect snapshot of an AC signal.
And because this is so incredibly useful, we actually have two ways to write this down. The first is rectangular form. It's like giving driving directions. Go this far on the real axis, then turn and go this far on the imaginary axis. This form is absolutely perfect for adding and subtracting. Then there's polar form, which is more direct. It just gives you the straight line distance from the center and the angle, and this form is a lifesaver for multiplication and division. Having both makes the math incredibly flexible.
So now we've got our perfect tool. It's time to put it to work. We're going to use this complex number system to build one single, powerful idea that describes how resistors, capacitors, and inductors all behave in an AC circuit, and that concept is called impedance.
Impedance, which we write as the letter Z, is basically AC resistance, but it's so much more than that. Because it's a complex number, it doesn't just tell you how much the circuit fights against current flow, that's just its magnitude. The number's angle also tells you exactly how that component shifts the timing between the voltage and current. It packs two crucial pieces of information into one elegant number.
This slide right here is your cheat sheet. This is the key. We can now describe each component with a single complex number. A resistor? It just resists current, no time delay. So its impedance is just a simple real number, R. But inductors and capacitors, they cause time shifts. An inductor's opposition makes the current lag the voltage by 90 degrees, which we can represent perfectly with a positive J. A capacitor does the opposite, making the current lead by 90 degrees, which we represent with a negative J. The physics is perfectly captured by the math.
All right, I get it. It's a clever way to describe things. But I promised this would make the math simpler. Well, here it comes. This is the big payoff.
Just look at this. The old way, a tangled nightmare of sines and cosines for every single part of your circuit. The new way, if your parts are in a series, you just add their impedances. That's it. You add up the real parts, add up the imaginary parts, and you're done. Decades of brutal trigonometry just got replaced by simple addition. It's a total game changer.
And maybe the most beautiful part of this whole thing? The most fundamental law in all of electronics, good old Ohm's law, works perfectly with these new numbers. V equals I times Z. This one simple equation, now supercharged with complex numbers, can solve for voltage, current, or impedance, and it automatically takes care of all those tricky phase shifts for you. It's just so elegant.
So let's step back for a second. What's the big picture here? This isn't just some clever trick for a test. This fundamental shift from messy trigonometry to simple complex algebra is the bedrock of modern electrical engineering. It's what allows us to design the power grids, the communication systems, and the computer chips that our entire world runs on.
If you take only one single thing away from this explainer, let it be this. Complex numbers are the natural language of alternating current. They transform difficult, error-prone trigonometry into simple, clean algebra.
So let's recap real quick. Complex numbers are perfect for this job because they pack both magnitude and phase into one number. The J operator isn't some mystery, it's just a command to rotate 90 degrees. Using that, the idea of impedance, or Z, brings resistors, inductors, and capacitors all under one roof. And the amazing result is that complicated AC circuit analysis suddenly becomes basic arithmetic.
And that leaves us with one last kind of mind-blowing thought. This one mathematical idea, this elegant trick of using a second, so-called imaginary dimension to handle phase, it underpins almost everything we plug into a wall. So you really have to wonder, without it, would our modern electronic world even be possible?
Thanks for watching.